if you want to study mechanical engineering, and then you are not just only to use Newtonian mechanics, but also you have to learn so-called analytical mechanics. Analytical mechanics contain the two parts. One is called Lagrangian mechanics, and another is called Hamiltonian mechanics, and which both of them are very useful because unlike the original Newton's law, in particular Newton's second law of mechanics, and Lagrange and Hamilton both are very accomplished mathematicians who had used their expertise and plus Newton's calculus and generalize the Newton's second law, or even rewrite Newton's second law, but the idea is the same, okay, into a more compact and more versatile general form, mathematical form, namely the partial differentiation equations. Okay, so today I'm going to give you a brief introduction of these two analytical mechanics forms. Okay, so in Lagrangian mechanics, the basic equation of motion can be simply written as like this: the partial L delta x minus d dt partial L with respect to the x dot, which is actually the velocity, equal to 0. Okay, and what is L? L in this equation is called Lagrangians. So it is in general a function dependent on the coordinate x and the first derivative with respect to the time, the velocity, and the time. So that by definition, Lagrangians can be written as a function of the three variables. Of course, you may ask that what would be exact form? Well, Lagrangian is very relevant to the energy in a mechanical system, but a slight difference. By definition, Lagrangian is equal to the kinetic energy of the total kinetic energy minus the total potential energy. So that is slightly different from the total energy. Okay. And bear in mind, when we study analytical mechanics, we would prefer to describe the motion of the particle or many particles in terms of their coordinates and the momentum. Okay, so therefore, sometime whenever we encounter the velocity x dot, we can also replace that by a momentum apart from the mass. Okay. So this is the basic equations to apply Lagrangian mechanism. So in practice, what you need to know is just simply find the kinetic energy. Okay, the kinetic energy for the particle can be written as you have learned before in high school, equal to half mv squared. And in addition, we can, as I explained before, because we would prefer to use momentum rather than velocity to describe the kinetic energy. So you can sometime, or in many cases, we can rewrite this formula as p squared divided by 2m. Okay, so that is only differences is in form, but physically they represent the same thing. The kinetic energy. And the potential energy have a different form. In this particular example, can we just consider that the gravitational potential energy near the surface of Earth? So in this case, the potential energy can be simply written as mgx. Okay, in order to use this coordinate, we have to draw this diagram here. So this is a diagram I'm going to use to explain this. Perhaps put it here. So this is ground. This is ground. The vertical axis is our coordinate. You can consider this just as one-dimensional motion. So if the object stay here at position x, and this is ground, at this position, the potential energy EP can be simply written as mgx. Okay. You see, when we use analytical mechanics, we barely pay attention to the force in the first place, right? We started from energy. Of course, if you do want to know the force in this simple case, we can add it as force, because this is important, because eventually we are going to compare with analytical mechanics with their original form, namely the Newton's second law. So let's just put the force there. So that is force downward. So that force is called gravity. So the force downward is negative because downward, mg. And that's it. Of course, this object may have certain velocity, say upward, or downward, or it could downward. So at this particular moment, we just assume that the velocity, instantaneous velocity, is upward. So what can we describe? We can either use x dot, which is means the first derivative of the coordinate with respect to the time. Or you can just describe these upward vectors by using the momentum, by using momentum. So that is equivalent. If you use momentum, then that just can be written as the product of mass and the linear velocity. Okay. So let's just use this simple example to illustrate how do we apply Lagrangian mechanics. Okay. So if we just follow this mathematical form, we can simply obtain these two different first partial derivative. Okay. First, let's just work out so partial derivative L partial to the x. Okay. So if you return to the form of Lagrangians, then we see that kinetic energy is independent of x. Okay, so the first partial derivative is 0. So the only non-zero term is the second one, the potential term. So potential term is mx. So if you take into account of the sign, we simply get mg. Okay, and then we consider that partial derivative first, that namely the der Lagrangian, and the partial x dot, which is velocity. Okay, so if you use this form here, so we know that velocity is exactly equal to the first derivative of the coordinate. So then from there, we just get that, so half, so that you use some calculus, we can obtain the m, and then the v, and v dot. V dot just can write as the second derivative. Okay. Second derivative. Sorry, it's still just first derivative. It's first derivative. Okay, first derivative. And later, then we have to use the differentiation with respect to the time, the second time. So if you substitute that into, if you just follow this one, we will substitute this equation. Eventually, we got so based on this calculation, we can obtain that the first term is negative mg, and the second term is just equal to mx second derivative with respect to the time equal to 0. Can you see what's that? What's this equation? If you just rearrange that one, we will get something like this. We got this very familiar form in high school physics. The m time acceleration equal to the force. So this is exactly the Newton's second law, ma equal to f. So from this simple example, you can see that Lagrangian mechanics, although it's very general and versatile compared with Newton's second law, but they are equivalent. So Newton's second law is at the core of this generalized analytical mechanics. Briefly, let's talk about the Hamiltonian mechanics. Okay, unlike the basic equation of motion, in Hamiltonian mechanics, the general equation of the motion can be simply written as a pair of differential equation. So one is first derivative, the velocity. One is x dot, can be written as partial derivative. So this is called Hamiltonian. With respect to this time, we have to use momentum. So that is P, okay. And almost symmetrically, we can also written as the first derivative of momentum with time, P dot, can be simply written as a negative partial derivative of Hamiltonian with respect to the coordinate. Okay. So that are the two basic equations of motion in Hamiltonian mechanics. Of course, you will ask, what is Hamiltonian? Well, Hamiltonian compared with Lagrangians is closer to the energy. By the way, you can just consider that Hamiltonian is simply the total energy of the system. Now here I just, in this simple example, we just consider a single particle system. So we don't have to summation. But in general, in many cases, when you actually apply Hamiltonian mechanics, you can put the many term. So many particle, many component, many rigid body, for example, involving rotation, involving the oscillation, and the forced vibration. So it will be very useful, both of them. Both Hamiltonian mechanics and Lagrangian mechanics are more practically useful than the Newton's second law in his original form. So how do we apply the Hamiltonian mechanics? Well, first of all, we can borrow the formula for the kinetical energy and the potential energy, right? So in other words, in order to find the first derivative of the coordinate, which is speed, by the way, this is speed. So the speed or the first derivative of the coordinate with respect to the time can be written as a partial derivative of Hamiltonian with respect to the p. Now in this case, we have obliged to use the kinetical energy in the second form, in this form. So if you do the first derivative with respect to p, what you can obtain? we just get m. Can you see? We just get we got 2p and divided by 2m. Okay, right? So in this case, what we have obtained, we got this p over m equal to m. So this is just exactly the definition of the linear momentum. So if you just multiply m on both sides, we get p equal to m multiply the velocity of the particle. Okay. So the first equation of the Hamiltonian mechanics, simply in this case, to give a definition of the linear momentum. Okay. So which is consistent with the Newton's mechanics. On the other hand, this first derivative of the momentum, okay, according to Hamiltonian mechanics, can be derived by the negative, so partial derivative of the d delta partial derivative with respect to the coordinate x. Now, in this case, the kinetic energy is independent of the coordinate. Actually, the kinetic energy term is always independent of coordinate. Okay, when you actually start the system with more than one particles, then the interaction among the different particles can be taken into account in the potential energy form. Okay, not necessarily potential energy, but also there's what's called a Lagrangian multiplier. Okay, we'll talk about that more complicated cases in the next video. But can we just finish that this partial derivative? So with h is Hamiltonian, the first kinetic energy is independent of the coordinates. Hence, its a partial derivative with respect to coordinates is 0. So we still can use the formula for potential energy. We can share this formula. So the partial derivative of Hamiltonian with respect to the h will simply equal to mg. Okay. So what does that mean? Well, if you just revisit Newton, so this if you just rewrite it for what we have, we got negative mg equal to dp dt. Okay. So this is not surprisingly is exactly the form of the Newton's second law, because in this case, F equal to mg. What is dp dt? dp dt, if the mass is assumed a constant, is exactly equal to m, and v first derivative. So this is Newton's second law. See, Newton's second law. So in general, Newton's second law, this is more general form of Newton's law. We have the total force acting on the object, in this case, a single particle, equal to m multiply the acceleration. Now, the acceleration in this case can also be written as m to the velocity vector. Okay. So this if you, by definition, you can also simply written as the first derivative of momentum. So this is Newton's second law. I just highlight this Newton's second law, which is at the core of both Lagrangian mechanics and also Hamiltonian mechanics. So I write down here. So this is a relation between. So this formula here, different form, is called Newton's second law. Newton's second law of mechanics. And I hope this brief introduction will give you some direction, and before you actually to study your analytical mechanics at university. Thank you.